In this video, we'll finish up section 13.10 with two more examples. This method doesn't get any crazier or anything like that. I'm just going to show you maybe how to solve in case some sticky parts come up. So we have this function. Now, why this method is fantastic compared to the last section is in the last section, what we would have had to do is solve this for one of my other variables, like z or x or y, and then plug it into here and then run the same method. So, sorry if you guys can hear my barking dog. I'm going to set up my two functions. I got f, x, y, z. That's a typo there. And I got x plus 2y minus 2z. And then I have g, x, y, z. And we get x squared plus 2y squared plus 4z squared. All right, so I have my two functions now. I need to find my gradients. So the gradient of f, first one's with respect to x, I got 1, and then I got 2, and then I got -2. The gradient with respect to g is going to be 2x, 4y, and 8z. All right, so we have our two gradients. We know now that we can set them, they are scalar multiple each other, so we're going to have 1, 2, -2 times lambda equals lambda. Let me fix my handwriting here. Equals lambda times 2x, 4y, and 8z. So we have three equations here. I got 1 equals 2 lambda x. I got 2 equals 4 lambda y. And then I have my last one, which is -2, 8 lambda z. I'm going to solve each one of these for x, y, and z. So I get 1 over 2 lambda. Y, I get 1 over 2 lambda. Again, it reduces to that. And then z is going to be a -1 over 4 lambda. We approach this the same way. I take my constraint equation because that's what's going to define the x, y, and z for me. They have to be in that equation or in that curve. So I take x squared plus 2y squared plus 4z squared equals 1. That's my original problem. And I'm going to plug all that in. Okay, so I got 1 over 2 lambda squared plus 2 times 1 over 2 lambda squared plus 4 over -1 4 lambda squared equals 1. I'm going to work this out. So I got 1 over 4 lambda plus, it's going to be 1 over 2 lambda. Oh, these are squared. And then the last one's going to be a positive 1 over 4 lambda squared. This still equals 1. If you multiply both sides by 4 lambda squared, we get 1 plus 1. That one's actually going to be a 1 plus, 2 plus 1 equals 4 lambda squared. I just multiplied both sides by 4 lambda squared. That gets me 4 equals 4 lambda squared. We can work this out, and we'll see that lambda is plus or minus 1. So now I just go through each one. Okay, so lambda is positive 1. If lambda is positive 1, we just plug them into our x, y, and z right above here, these. So if lambda is 1, I'm going to do this pretty quickly, is 1/2, y is 1/2, and z is -1/4. So if I were writing my critical points, one critical point would be 1/2, 1/2, -1/4. Right? I'm going to do f here, plugging it in. If I plug in those points, I get a 2. All right, now doing lambda equals -1, and we're plugging that back into x, y, and z. I get x equals -1/2. It just flips my signs. Y equals -1/2, and z equals a positive 1/4, which means the other critical point is -1/2, -1/2, and positive 1/4. This will spit out a negative 2. So we have a max of 2 at that point and a min of negative 2 at the other point. It's really nice when we get 2 points because we actually get the max and min, just shows it. This method, even though I think this part may get a little annoying, that part where we're actually trying to solve, but comparing it to the constraint problem, if I would have had to solve this original problem for z up here, I would have had to solve this for z and then plug it in and then run the method from last time, from last section. This Lagrange stuff is fantastic. It works really nice, especially when we're dealing with a 4D surface. Or we wouldn't call it a surface. I guess we don't know what it is at that point. All right, I got one more example for you. Let me stop my barking dog. Sorry for this, that it's in the video. He is annoying. Okay, thanks, guys. I apologize. He's just protecting the yard. All right, so here's this extrema. Again, xy. We don't have a z in this case, so we could use what we did in last section. Let's try the Lagrange stuff. So I have f of xy is equal to x squared plus xy plus y squared. And then g of xy is the constraint, but as a level curve, so we'll call it x squared plus y squared. All right, so the first thing, we know that the gradient of f is equal to some lambda times the gradient of g. So we just have to find each one. So let's find the gradient of f. So we get 2x plus y, comma, and then we do it for the y. I get 2y plus x. So that's f. And then the gradient of g, we get 2x for x, and then 2y for the y part. All right, so we just set this up. All right, so I'm going to set these equations up. I got 2x plus y, 2y plus x is equal to some lambda times 2x and 2y. All right, so I get two equations here. This one's a bit tricky, so this is why this example's in here. 2x plus y equals 2 lambda x, and then we also have 2y plus x equals 2 lambda y. So what we're going to do, let's solve this equation for y. So I get y equals 2 lambda x minus 2x. So y is equal to 2x times lambda minus 1. I'm going to go ahead and solve this one. X is 2y, and this works the same way, so lambda minus 1. I skipped a step there. Go ahead and subtract 2y over and factor out 2y if you want to see how that works. Now what I'm going to do is I'm going to take this whole portion here. Let me change that because it's so harsh. I'm going to take this portion here, and I'm going to plug it in right there. It's equal to y. So I get x equals 2 times 2x times lambda minus 1 times lambda minus 1. All right, plugging that in. I am going to start solving. So we have x equals 4x times lambda minus 1 squared. I hope you guys can see that. I divide by x. I can go ahead and divide by 4 too. So I got 1/4. The x's are gone. And I get lambda minus 1 squared. If I take the square root of this, I'm going to go up here. I get plus or minus 1/2 equals lambda minus 1. So I get two lambdas here. I got lambda equals 1 plus or minus 1/2. So the first lambda, so let's do that over here. Lambda 1, we'll call 1 plus 1/2, which is 3/2. And then lambda 2, we'll do that in a moment. So doing lambda 1, remember that, let's hold on one sec. If I let's look at y equals, so back up to this equation here. Let's do y equals 2x times, and we're going to plug lambda in, 3/2 minus 1. That is, if I minus 1 from that, I get a half, I get x. So with this lambda, y equals x. So what we're going to do here is we'll take our constraint equation, x squared plus y squared equals 8, and I'm just going to plug in that substitution, x squared plus x squared, because I'm replacing y with x, equals 8. That is 2x squared equals 8. If I divide, I get 2x squared, or sorry, the 2, let's divide the 2. X squared equals 4, which means x is plus or minus 2. I'm going to do it this way because we need two y's for that. So if x is 2, well, according to y equals x, y is 2. So that's one of my critical points. And then if x is negative 2, y is negative 2. So there's my other critical point from that. So here are my critical points. I'm going to make a list. I'm going to have 4 here. 2, 2, negative 2, negative 2. I know we have 4 because how the other one's going to turn out. So that's how we used 1 lambda from here. Right? And I'm going to use the other lambda 2 now. Lambda 2 equals, okay, that's 1 minus 1/2. That's going to be a negative, 1, no, it's not negative. 1 minus 1/2 is just 1/2. Right? I plug into the equation, y equals 2x times, and I put 1/2 for lambda. All right, this is back on this yellow equation here. All right, so we get, okay, 1/2 minus 1 is negative 1/2. I'm going to get negative x. So that tells me y equals negative x. I'm going to plug that in. If I plugged it back into this equation, x squared plus y squared equals 8. If I plug a negative x in for y, I'm going to still get 2x squared equals 8, which means x is a plus or minus 2. So again, we have that. X is 2. X is negative 2. And we are going to plug that into this equation right above. So y is negative 2. And then on the other one, y is positive 2. So there are my last 2 points. So the other critical points are going to be 2, negative 2, and negative 2, 2. I'm going to move this down here. All right, so we can actually get the function values by plugging it back into the original f. I'm going to save some time on this video. If I plug in 2, 2, I get 12. If I plug in negative 2, negative 2, I get 12. If I plug in these final points, we both get the same thing. So 4, so we have a minimum of 4 at both of those and a max at both of those. It's a really neat method. This one's a bit tricky with the 2 lambdas and plugging them back in and how to get all those points. But it's truly the same process. We just have to do more. So this is all of 1310. It just allows us to optimize when there is an x, y, and z, and it's just another method to optimize a function using the gradient.